Good afternoon, everyone. Welcome to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson, the site director here at Green Bank, and just wanted to give you a brief update of what's happening at the observatory this week. So some good news is we think we've finally procured all the parts, or will soon procure the parts for the prime focus boom. So the last piece will be available to us mid next week, and we hope to effect that repair of the boom shortly. And that will let us change receivers and use prime focus receivers again and get back to kind of normal operations. Want to thank the crew, the telescope ops crew, for their hard work in getting all this done and navigating us through this difficult spot, but we're going to merge out the other end just fine. All is well here at the observatory. We had a nice workshop, the K-band at Green Bank, K-band Science at Green Bank workshop last week. That was a very nice meeting. Lots of interesting science happening with the ammonia surveys and other K-band science, the astrochemistry surveys. And it was good to see people on campus again discussing science, and looking forward, we have some ideas for how we may proceed with new instrumentation and new support. So kudos to Larry Morgan for running an excellent meeting, and thanks for everyone who attended both virtually and in person. Very, very lovely meeting and very interesting science. So with that, I'll hand it off to Dave Freyer, who's going to introduce this week's speaker. Take it away, Dave.
Hello, thank you. Our speaker today is our very own Jay Lockman, so he didn't have to travel far, and he'll be talking about high velocity, his work on the high velocity Smith cloud. So go ahead, Jay, you can take it away.
Hey, thank you.
Oh, I forgot to mention why he's getting his presentation. If you have questions, put them in the Q&A, which is the bottom of the, your Zoom window.
Okay. Let me get this on full screen. Okay, thanks very much. This presentation is unusual, and I believe that it's the first one in this series where the work has not yet been published or even submitted to the archive, but we had some schedule changes that caused me to fill this blank and talk about something that I've been working on recently with a few collaborators who are listed here: Bob Benjamin, Nick Pichette, who was an REU student, and Allison Ford, about the Smith high velocity cloud. First off, what are high velocity clouds? If you look at a map of the total hydrogen in the Milky Way, it looks something like this, with the bulk of the hydrogen in the plane of the galaxy. And then you see these large loop-like structures caused by supernova events and other energetic events in the galaxy. But if you put a filter on the hydrogen, a spectral filter, so you're just picking out a particular velocity, and you choose your velocity correctly, you'll come up with something like this. And this is based on data from the 1980s, but gets the point across quite well. You still see the plane of the Milky Way, but you also see this object down here that has a very unusual velocity for its location in the sky. This was discovered by a graduate student, Gail Smith, and published in 1963, before we even knew that there was a class of objects called high velocity clouds. So this in many ways is the first high velocity cloud. So what are high velocity clouds? These are regions detected so far primarily in hydrogen, but not solely, that cover a good fraction of the sky, and they have a velocity that is inconsistent with galactic rotation at their distance. Now, let me see if yes. Excuse me. For some of these, we understand why they are there. Here's the Large Magellanic Cloud and the Small Magellanic Cloud, and there's a huge trail of emission stretching over 200 degrees on the sky, the so-called Magellanic Stream. So this particular high velocity cloud complex is caused by gas being stripped off a dwarf galaxy as it interacts with the circumgalactic medium of the Milky Way. This emission here off to the left is also probably associated with the Magellanic Clouds. But there are these other complexes that picked up different names throughout the years. And I'm going to be talking about one of them located right down here in the right-hand side of the figure, the Smith cloud. We still don't know the origin of most high-velocity clouds. As I mentioned, some of them are gas stripped from other galaxies. It could be condensation and infall from the intergalactic medium, or gas being ejected from the Milky Way disk and recycled. In all cases, though, incidence of gas, either whether fresh or recycled, has a profound influence on the star formation history and future in the Milky Way. And we need about a solar mass of fresh gas a year to sustain the star formation that we believe has occurred over the last gigayear or so in the Milky Way. So high velocity clouds may be the link between the current state of the Milky Way and its future. Now I'm having trouble advancing. There we go. So here is the Smith cloud now as viewed from the Green Bank telescope in the lower left. And you can see that it has a very cometary appearance with fragments coming off to the side and appears to be headed right into the Milky Way. We came up with a model for it based on the kinematics of the cloud and some reasonable assumptions. This cloud has a well-determined distance from several different methods, so we can actually calculate things like its mass and its size. There's a few million solar masses of partially ionized gas. The trajectory that it's coming in on, illustrated here in this artist's conception, although the data for Smith's cloud is real data, indicates that it's going to be adding angular momentum as well as mass to the disk. This is an object which has some associated magnetic field, moderately low metallicity, and a number of people have modeled it as a dark matter subhalo, of which we're only seeing the baryonic component. Is it a dwarf galaxy waiting to be discovered? Many questions about the Smith cloud. Let's go back to our image of total hydrogen in the sky again, and now look at a 40 by 40 degree region that includes the Smith cloud, where we've asked the question, in this region, what is the emission that is going faster than permitted by galactic rotation? And that's where this figure comes in. You can see in the lower central part of the figure, Smith cloud right there. But also you see up towards the upper right, this band of emission, which seems to have the same position angle from the Smith cloud, but is right now in the galactic plane. I'm calling this the leading component because I believe it's connected somehow to the Smith cloud phenomenon. We used a new survey of the Green Bank from the Green Bank telescope of hydrogen over a large area to study this leading component. Now here again is the new data where we're showing the total hydrogen beyond a certain velocity, the total hydrogen that is not permitted by galactic rotation as a function of longitude and latitude. In the lower left is the tip of the Smith cloud here, and you can see this band that stretches up through like this. The GBT data go from 13 to 35 degrees, plus or minus 10 degrees in latitude, and then with an extension down just to pick up the tip of the Smith cloud. And to the right, we see a single channel map blowing up of the lead component. And you can see that a lot of the emission breaks up into discrete clouds. Here's another image at a different velocity showing some of the individual discrete clouds and how they look in spectra. You can see these bright features. We're not lacking signal to noise here, and they are distinctive and stand out by and large against the rest of galactic emission. So we came up with a catalog of clouds in the leading component. And the clouds, in order to make it into the catalog, they had to be low confusion. And by that, I mean that here's some examples of objects that in channel maps show up quite discreetly. But you see here, the spectra are blended with lower velocity gas. And it's really very difficult to pick out the properties of these clouds. So these are not involved in the catalog. In fact, we believe that we've calculated only a small fraction, cataloged only a small fraction of the total mass in this object. In order to be included in our catalog, the clouds also had to be located along the axis of the Smith cloud, which is this band running from lower left to upper right. So there are some clouds, if you can see my pointer, down here, which certainly have interesting velocities, and down here, but we didn't include these because we wanted it to definitely be along the axis of the Smith cloud. Clouds had to have a velocity that was not permitted by normal galactic rotation. And here is an example of what we expect for these clouds. The difference between what we expect for these clouds and their actual velocity, the amount that these clouds have a forbidden velocity, and that's given in the blue dots here. And we see that a number of these clouds have several tens of kilometers a second that passed what is permitted for normal galactic rotation at any location along their line of sight. And so this is another criteria. And finally, I will get to the last criterion, evidence of interaction with permitted emission, in a few minutes. Here's a sample of 38 unconfused clouds in the leading component. You see they're not particularly faint, column densities of say 10 to the 20th or so, diameters of a few tens of parsecs, assuming these clouds are 10 kiloparsec distance, masses, few thousand solar masses, and the density, which is just the column density divided by the diameter of a few tenths. Nothing particularly outstanding about any of these objects, except really their kinematics and their location. And here's a description of their kinematics. For looking over large areas in the galaxy, the local standard of rest velocity is really not very good because it contains several projection effects. So instead, we use the velocity with respect to the galactic standard of rest, which is the LSR velocity plus the circular velocity at the orbit of the sun times the longitude and cosine of the latitude, sine of longitude and cosine of the latitude. And in this figure, plotted against longitude, we see the local standard of rest velocity of the clouds, and then the galactic standard of rest velocity at the top. The median velocity of this group of clouds is shown by the solid line, and the velocity of the Smith cloud by the dashed line. And so you can see that it has a kinematics quite, when you take out projection effects, quite close to that of the Smith cloud. Almost all of these clouds appear to be interacting with the Milky Way's interstellar medium. And this is really key because it establishes that these objects are in the Milky Way disk. And here's example one right here. This is one of our clouds. In fact, this is the same cloud here as in the upper left. And you can see that there are these lower velocity spectral components identified here with the dashed arrow. And we believe that this is the site where this cloud is hitting normally rotating gas. On the right, we have galactic latitude versus velocity plots. Some of the clouds, the one in the upper left, for example, show these tails of emission going down to lower velocities, very consistent with the outer edges of this cloud being stripped off and decelerated as it encounters normally rotating galactic gas. And the location of the normally rotating galactic gas is often shown as a peak here at lower velocities. These are 4 examples. The majority of the clouds in our sample are interacting with lower velocity emission. And in the lower left, these clouds are indicated by red stars. So this is really important. Oh, I'm sorry. We see the same thing in the Smith cloud itself. And here's an image of the Smith cloud on the left. And if we take a position velocity cut across this red line, that's what's shown in the right. At a velocity of about 100 kilometers a second is the Smith cloud. But you can see that at its edges, there's material being decelerated down to normal permitted velocities. In some cases, whole clumps come off the cloud down to lower velocities. So again, it looks like the leading component is a phenomena very much like the Smith cloud itself. Once you have a velocity of an interaction site and its position, you can use a rotation curve to determine where that is in the galaxy. What I'm showing here is the velocity of our clouds minus the velocity of the Milky Way at their location. In other words, this is a measured quantity. This is the difference in velocity between the cloud and the material it's interacting with. And you can see in some cases it's quite high, over 50 kilometers a second. The median is around 44 kilometers, 45 kilometers a second difference between the velocity of the cloud. And so we can use the position and the velocity of the interaction to derive a location. And here's how it looks in 3 different projections. Let's take the lower center first, because this is the view from above. The sun is the blue circle here on the lower left, and the red crosses and star are various components of the Smith cloud. And all of these blue points in the center are positions that we think these sites of interaction of the leading component. 0, 0 is the galactic center. Viewed from the distance from the galactic plane, which is Z, and Y, which is distance perpendicular to the line of sight, we see the association of the clouds here. A lot of this correlation is really just simply the fact that there is a strong correlation between the longitude and latitude of clouds in the leading arm because of its orientation across the galactic plane. Now, what's also interesting in the lower figure, again, a top-down view on the Milky Way disk, is that our projected site of interaction of the Smith cloud when it hits the Milky Way is way over here where we see the black star. So it's not a simple matter to connect what's going on with the Smith cloud now from what's happening and where it's happening in the Milky Way disk at the current time. The velocity that we measure with respect to the galactic standard of rest can be decomposed into 3 components. V theta, which is in the direction of galactic rotation, VR, which is radially outward from the galactic center in the plane of the Milky Way, and VZ, which is vertically. Now, the first thing you can see when you look at this is that sine B is going to be very small. We're always within a few degrees of the galactic center. So VZ to first order will not have a great effect on the velocities we measure. Not only that, there are places in the galaxy where the longitude and this azimuthal coordinate they combine to make the cosine term about 0. So in that case, not only are vertical velocities minimized, but radial velocities are minimized. And at these positions, we can really determine what the circular velocity of the incoming clouds are. And so here you see cosine L minus theta, where it's about 0. We see 240 kilometers a second as a measure of V theta. That can then be used to plug in and solve for VR, again, assuming VZ sine B is small. And we get radial components of about 60 kilometers a second or so with a big error. These dashed lines show what a 10 kilometer a second change in V theta does to the derived VR. The table in the right summarizes. For Smith cloud, we believe that the motion in the direction of galactic rotation is 270 kilometers a second, radial motion about 100, vertical motion 73, moving up north toward the galactic plane. And so our estimate for V theta for the leading component is 240, and for a radial component, 65. We really can't determine the vertical component with any accuracy at all. Now, these are close enough again, considering all the uncertainties that go into this analysis, to once again make us feel that we're on the right track in saying that the leading component is certainly in some way connected to the Smith cloud phenomenon. So to summarize, we found what we believe is a leading component of the Smith cloud. It has about 1 million solar masses of hydrogen. It's difficult to determine because of blending with lower velocity gas, but this is a good estimate. It's interacting with disk gas. I didn't mention it, but it's about 10 kiloparsecs away from the sun. It's also adding mass and angular momentum to the Milky Way disk, and it has kinematics consistent with that of the Smith cloud. So maybe it's appropriate now to call it the Smith stream. Is this the fragmentation of a much larger structure? I mentioned earlier that the Smith cloud had been modeled as the baryonic component of a dark matter subhalo. But it's clearly, the situation is a bit more complicated than that. In fact, the orbit of the Smith cloud is quite shallow. And if our understanding of its kinematics is at all correct, then it must have passed through the galactic plane in the anticenter sometime in the past. How does something like this survive a passage through the disk? In fact, even now we see that it's being torn apart by its interaction with the circumgalactic medium, and for the leading component, being disrupted by its interaction with the gas in the disk. I think we have a lot more to learn about this fascinating structure, which has been in some ways hiding in plain sight in hydrogen data in the Milky Way for possibly 60 years. Thanks very much.
Thank you, Jay. Participants or people are online, feel free to put in, oh, we have the Q&A questions coming in, put in the questions in the Q&A. So Jay, the first question, would the leading component of the high velocity cloud colliding with the galactic ISM slower gas create a potential shock front that would precipitate star formation?
Yes. You know, it's colliding at a very interesting longitude, certainly where we do see lots of star formation. And this is not too different than, well, it's very different in location. Let me go back to the views, which all of a sudden, there we go. So I don't know of any particular star formation. And actually, I haven't cross-correlated it with regions of star formation in the galaxy. So I should just say that is certainly something to do. Okay. It's a very interesting question.
Okay, next question, and thanks for sharing these very interesting results. How do you know the features bridging the high velocity clouds to the gas in the disk are deaccelerating gas and not accelerating gas?
Yeah, so this goes for the Smith cloud as well. And let me just, I'm having trouble with this. Well, here's the Smith cloud, okay? I say decelerating because you could imagine, and in fact, the Smith cloud has been modeled as an object which has been ejected from the gas, in which case, by a fast wind, for example, in which case you would expect its edges to be higher velocity rather than lower velocity. And so we see then in the bridges, again, the same sort of thing. This is material at the edges has a lower velocity rather than a higher velocity. And so it's, you know, if it were a wind, it would be coming from a high velocity direction. And so I think that we can be pretty sure of the direction of the phenomena.
That makes sense. Thank you. Then we have a comment thanking you for your nice talk. Do we have any additional questions? Or, oops, sorry. Thank you, Elizabeth, for putting in another question. And her question is, if it is the survival of a previous passage, would there be expected traces along its path? If so, is it plausible to search for these traces?
That's an excellent question. And in fact, a project with Tony Minter is underway to do just that. One thing which is certain now is that the Smith cloud extends much further down to the lower left than is evident in the figures I've shown here. We have a cloud that's at least 10 degrees behind the main body of the Smith cloud that shows every evidence of being associated with the phenomena. Beyond that, it gets a little tricky, but certainly the cloud itself is probably at least twice as large as the images we've shown so far.
I just want to follow up on that, Jay. There's not a stellar, is there a stellar component ever detected with the Smith cloud? Because in terms of infrared colors, I know with the large scale 2-mass survey, they can almost see streamers and stuff based on colors. Okay.
Yeah, you know, here's some properties of it, and no stars that we know of. And this was work by David Stark, but it is now 7 years old. And I think this is an area that would be a fruitful source for future research, to really look deeper. And now that we have the Gaia data, to really ask the question, is this completely free of stars? But as far as we know right now, there is no stellar component.
Okay, thank you. A couple more questions have come in. Do we know what the magnetic field orientation along the cloud is?
Yes, there are two papers by that, one by Hill and the other by Betty more recently. It appears to be wrapped around the cloud as if the cloud was perturbing the magnetic field of the circumgalactic medium that it was moving through. And as I say, the Betty et al. 2019 paper has all the details on that, based on analysis of Faraday rotation of background continuum sources.
Another question, can a high velocity dark matter mass have I'm sorry, excuse me. Be mass captured. Okay, can a high velocity dark matter mass capture the gas and draw it in with it, basically?
Oh, fascinating question, because this is something that Robin Shelton and her students have been working on at the University of Georgia, dropping a dark matter subhalo through the Milky Way. There's to some extent an exchange of gas between any gas that was in the subhalo beforehand and matter it picks up from the Milky Way disk. And in this regard, the metallicity, which is kind of unexpected as being roughly half solar, might be a big clue that that's exactly what has happened here. Again, let me refer you to Robin Shelton's papers and those of her students.
Okay. David Stark chimed in about the stellar component, and he was saying that we look for star formation with the UV, not the old stars, and is emphasizing that should be done. We should be looking, checking for the old stellar populations associated with this.
Yeah, excellent point.
Okay. Whoops. Oh, got another question. What was the cloud originally? They're just asking your opinion. What was the cloud originally, and what are the possibilities besides what you've mentioned already? So what do you think, and what are the other possibilities?
Well, it looks, if you just look at the Smith cloud, it looks a lot like a dwarf galaxy coming into the Milky Way. But the presence of the leading component, which probably has as much gas as the Smith cloud, at least within the uncertainties, I don't know what it was. It's very attractive to think of it as a dark matter subhalo, which is maybe being tidally stretched or fragmented as it's approaching the disk. But I don't know of any theoretical work that's been done that's appropriate to answering that question. It's just very puzzling. Okay,
a comment saying a great observation for a JWST, and I agree. Do some near cam observations.
All right. All right.
I'm not sure when the next proposal deadline is coming. I think in January or so. And then we have another question. Is the metallicity of the leading edge the same as that of the main cloud?
Okay. The metallicity is from Fox et al. 2016 and is based on 3 background objects. And there are certainly uncertainties in the determination of the metallicity toward each of the objects. And that's reflected in the range I give here from 0.3 to 0.8 solar masses. Some people have tried to fit a straight line through these 3 points and claim to see a metallicity gradient. Mm-hmm. I would like to hold off until we can get more spectra.
Okay. Out of curiosity, which way would the metallicity gradient go?
I wish I could remember, but I think it may be head to tail. I can't quite remember.
Okay, that's fine. No, I was just sort of curious. And I think we got all the questions that come in. I'll wait just for a little bit, and thank you again, and wait for any more final questions to come in. So seeing none, thank you very much, Jay, for your excellent presentation on the Smith cloud. It's always nice to see the results here. So everybody have a great day. We're going to be signing off. Now, I think the speaker for next week, the next community Zoom is still at TBD, unless Jay.
Right.
Okay. So Are you reaching out for people? So if people are online and have a GBT result they want to share with the community, please contact Jay. He helps coordinate these. So thank you very much. Okay, we'll see you, Jay, and everybody. Bye.
Thanks. Bye.